Welcome everyone to this mini symposium to get to know our new assistant professors who were recruited recently in WACQT. So we have Mizanur Rahaman, Adam Kinos, and David Busto. Adam and David have already started, while Mizanur will start in March 2025. Mizanur is our first speaker. So he is currently a Marie Curie Fellow at École Normale Supérieure in Lyon. And he obtained his PhD from University of Regina in Canada, and then was a postdoc at University of Waterloo in Canada. And finally, so was also before joining WACQT, and before getting the Marie Curie, he was assistant professor at the BITS Pilani Goa campus university in India. Then the floor is yours, Mizanur. Thank you very much. You have 20 minutes.
Thanks a lot. Thanks a lot, Julia, for giving me this opportunity to present my research here. And thank you all, the WACQT members, to be present here. Yeah, so I will talk about my research, but before I get into the detail of my research, let me tell you a little bit about my background. So I am a mathematician. And my area of expertise is in operator algebras. So my general theme of my research is to use my background in operator algebras to solve problems related to quantum information theory. So to give you some ideas, operator algebras is a branch of mathematics that study linear operators on Hilbert spaces, finite or infinite dimension. So historically, it was invented by John von Neumann to lay out the foundation of the mathematics of quantum mechanics. And over the time, since it's invented, it took a life of its own. It became a very major active field of research in mathematics, very purely mathematical reasons. But since the advent of quantum information theory, since 2000, there has been a significant overlap between ideas from operator algebras and many challenging problems in quantum information theory. So today, what I'm going to show you is some of my contribution to the field of quantum information theory using this background of operator algebras. So as it turns out that many challenging problems in quantum information theory are deeply rooted into some challenging problems in operator algebras. And the goal is to address these problems and try to resolve them. So largely my past research has been focused on these three wheels, if you may like. So the first one is studying entanglement and non-locality. The second one is quantum communication over long distance. And the third one is how quantum information theory behaves in a continuous variable setup. The entanglement and non-locality is very theoretical, and there's many wonderful applications of operator algebras that we witnessed over the last decade. But for this particular talk, with the WACQT members in mind, I would mainly focus on quantum communications, the aspects with quantum communication and the continuous variable relation. So let me go to the first part of the talk, which is quantum communication over long distance. So as you know, any physical realization of a quantum computer is likely to be susceptible to errors, right? Noise and inaccuracies. And so a general aim of this topic of my research is to understand how noise propagates over time, and build efficient algorithm or method to mitigate the problem that occurred by noise. Now, obviously, as we know, that the main challenges is to understand how decoherence, how deep, how decoherence occur, and how the decay of capacity of various channels evolve over time, and what's the quantification. So, I mean, if you pin down this problem more specifically, what it boils down to is that when your open quantum system is evolving under a noisy quantum channel, intuitively it's clear that there will be some point after which the channel would lose all its capacity. So all its information transmission capacity, both classical and quantum. Now the question is, what is the time? Can we pinpoint the time after which this would be useless, so to speak? And this was actually came up as a conjecture. It's called VLAN conjecture. Give rise to Garcia, Westrate, Wolf, and Sirac. And it's still an unsolved conjecture. It's very mathematical in the way it's posed, but it has many connection with quantum many-body problems and also tensor network. And so, so one of my research outputs in this direction was I was able to solve this conjecture for unital noise model. So if your quantum channel happens to be unital, there's some special spectral characterization that I was able to use to bound this the index. So this means after this index, the channel would be useless, and the index has to do with the dimension on its on which it is acting. So if the dimension of the system is d, the upper bound I provided was 2 times d minus 1 squared. And this is a sort of an universal bound because it works for every noise model that you can work with. So it doesn't fully solve the conjecture because it is only, but it provides that the conjecture, which is on the big order of d squared, is true for many quantum channels. And to achieve this, as I mentioned, I used some operator algebraic properties associated with a unital quantum channel. Continuing this line of work with a collaborative group in Cambridge, we are formalized, like we are able to establish a formal study of capacity decay of quantum channels. So zero error, we mainly focused on zero error because the theory is clean, but the methods that we developed could be studied for arbitrary error that you are interested in, arbitrary capacity error. And we also found an algorithm for some specific channels that you can build quantum and classical, that you can actually store your classical or quantum message that would be protected against the entire evolution of time. So suppose you have a quantum channel, it's evolving under iteration, and we were able to find a way to store classical and quantum messages for some particular class of channels, that those would be protected under any evolution or any application of that channel. So those would be protected under the entire time span. So it's like a more Shannon theoretic aspects of looking at it. The second aspect of the same theme of quantum communication is what's known as the PPT squared conjecture. So again, here the goal is to transmit information over a longer distance, but because of the no cloning theorem, you need these quantum repeaters. So you basically use this entanglement swapping procedure to transmit information from one place to another. If it's really a long distance, then you use it again and again. Now, for some practical purposes, the quantum states that are used for this repeater protocol was PPT states. But every time they use this protocol of entanglement swapping, they notice the 2 PPT states give rise to a classical. Like after this entanglement swapping, you are not getting any quantum advantage. The states become separable. So there's no quantum advantage. And actually, this led Matthias Christiandel to propose that is it the case always that when you take 2 PPT states, do this entanglement swapping procedure, do we always get separable? If the conjecture is true, then there is no advantage at all. Again, this conjecture is still an open conjecture. People are working on it, and it will be very useful to know that whether it's true or not. But turns out that this is the way the conjecture is formulated, and if you find an equivalent way, it's a highly mathematical, challenging problem of operator algebras. So with the collaborative group in Waterloo, what we showed is that it does become entanglement if you do it sufficiently large enough. So not for two repetition of a channel, but if you take a PPT channel, so you transmit the problem from states to channel, and if you compose it enough time, then at the end of that finite time, you're bound to be getting a separable state. So in all practical purposes, what our result shows is that PPT states are useless for this particular protocol, because in practice, you're not going to do it just once. You're going to do it many, many times, this quantum repeater. And we show that at some finite time, your state would be separable. So you won't get any quantum advantage. So that's somehow providing a limitation of quantum repeaters, if you will. So these are the two main highlights from the quantum communication of a long distance area. But note that all the results that I showed or the problems that I discussed are based on discrete variables. So basically qubit setup and very finite dimensional setup. But then there's this other paradigm of quantum information or quantum computing that based on infinite dimension. And I'm going to talk a little bit about that in the next few slides. So here, what we are mainly focusing on is how entropy behaves in infinite dimension, mainly in continuous variables. So imagine you have a large system that are built up with small little systems, and what you're interested in is calculating the global entropy of the system. Now, a general approach is you have a very large system. So all you can do is, if you know the entropy of the smaller parts, you'd like to sort of add them up, glue them together, and say something about the global entropy. It's not always true. And then a big question in this field is to know for which state this is true, that you can somehow add them up to some error to get a hold of the global entropy. So the two questions that comes, this is the general theme of the area, why entropy and why infinite dimension? So first of all, let me give you an example of why we are interested in entropy. Well, entropy shows up in every fundamental task that you're performing, both classical and in quantum information theory. Like, for example, hypothesis testing or data compression or quantum key distribution. Entropy provides this optimal efficiency with which you can perform these tasks. And you would like to know how entropy behaves if your system is, let's say, modeled by an infinite dimensional Hilbert space. So it's very natural to study entropy in the context of infinite dimensional Hilbert space. Why infinite dimensional to begin with? Well, as I told you, there's two models from finite dimensional and infinite dimension. To some people, actually, continuous variable is more natural because it is more adaptable and amenable to the standard telecom technology. It provides more quantum gates in implementing quantum algorithms than which are not available in the discrete variable case. So continuous variable turns out to be a more practical paradigm to work with. And so if you are analyzing your system over continuous variables, then these basic questions of entropies, how entropy behave in infinite dimensional Hilbert space, comes very naturally. So the very specific problem that we have in mind is we should be able to carry out these fundamental tasks like hypothesis testing, or let's say quantum key distribution or randomness extraction, but we'd like to do it not only in finite dimension, we'd like to do it in any generalities possible, so infinite dimension and beyond. And so how do we do it? Most of the techniques that we have so far are based on finite dimensional paradigm. And so the effort is to push these things into infinite dimensional setup. So the first important cornerstone of this area is Shannon's equipartition property, asymptotic equipartition property, that tells you is that Shannon entropy is, in some sense, provides this fundamental limit of all these tasks of data compression and hypothesis testing and etc. This result is a classic result in information theory and has been generalized to the quantum setup. and many applications have been found, but still in the realm of finite dimensional setup. So the goal for this area is to investigate what happens if we allow infinite dimension. So it immediately brings a lot of pathologies and technical difficulties. First of all, known techniques of these proofs of all these analysis don't work. And entropy is very difficult to study in the infinite dimensional context. So this has been an effort, which is still an ongoing effort for me over the last few years, that to realize some of these landmark theorems that are very heavily used in the finite dimensional context, how can we realize this in continuous variables? So not only in infinite dimension and also beyond, in the sense that more algebraic setup. So for AEP, we were able to successfully extend this result in using some operator algebraic tools into infinite dimensional Hilbert space, and also in the setting where in a more abstract as possible, like quantum field theory and quantum algebraic formulation of quantum theory. So this result does hold, and it comes with a lot of interesting application. And what we prove is actually stronger than this. So we can say things which are beyond IID states. So even more non-IID setup, we can establish this theorem. And one of the crucial application that is more important to this device-independent cryptography, which was the original goal or original aim, is this entropy accumulation theorem, which is also we're able to extend. This would be a forthcoming paper that will come up very soon. And this is the project. For this project, I was awarded the Marie Curie fellowship, and I'm still pursuing this project. The theoretical part of it has been more or less achieved. And we are now working on how to apply this theoretical result into the practical scenario. And this would be my future goals that I would soon develop. But just before going to the future work, just want to mention that it's also provided me an opportunity to go to the Science is Wonderful, a small little workshop to share my research with high school kids last March in Brussels. Very quickly to go to the future research project. The first one is this, that security proofs in quantum key distribution in continuous variable. So the reason that I was interested in entropic equipartition property is this, that in the finite dimensional quantum key distribution or device independent quantum key distribution, that result is very important. I think the equipartition property, because it provides better security proofs. In the continuous variable, it's a very difficult task, and the challenge is not conceptual, it's more technical, because you are dealing with an infinite dimensional Hilbert space, and it's not very clear how to use them to provide better security proof. And that's the theoretical part that we developed, and hopefully this would bring some new insight into the security in the CVQKT protocol. This is the first work project. The second work project is based on the resource theory beyond coherence. So quantum coherence is a resource that are heavily used in finite dimensional quantum computing. They're related to understanding reversibility of state transformation and also quantum speed limit. And a recent work of mine provides a way to talk resource theory of coherence beyond finite dimensional. But we have to. There's some natural plethora of problems that come with it, and one of my near-term and long-term project is to investigate this theory and come up with the reversible theory of coherence beyond finite dimensional setup. And I think I know it. 2 minutes short. So the last one is again with finding out capacities or dynamical systems. But so far the analysis we did and we're able to succeed are all in the setup of finite dimension. It will be really interesting in the continuous variable setup to find an algorithm to protect or to design an algorithm to have classical and quantum message that are protected against the entire evolution again. This would be a very nice thing and more practically amenable. So these are the 3 projects that I have in mind, and I hope that once I am in WACQT, I will be able to expand my network with all the members with WACQT and be able to collaborate with all of you in any capacity that's possible. I'm very open to learn new things, as I'm a mathematician, but I'm also very, very open to the physics and the experimental development. And I'm hoping that I will take my opportunity, and it will be a great time for me to go to WACQT and meet you all and talk science. So with this, I thank you very much for your attention, and I just leave with you with some collaborators, which I really thank for my research, still date and future as well. And I conclude my presentation here. Thank you for your attention.
Thank you very much. So on behalf of everyone, I applaud.
Hope it's not, I didn't know what time or.
So we have one question. So now you were good on time, Mizanur. Thank you.
Okay, good.
We have Yaran wants to ask a question. Yaran, please.
Oh, yes. Thank you very much for a very nice presentation. And I'm really glad that you're joining us in WACQT. So I had this, you mentioned your work on capacities of quantum channels.
Right.
For finite dimensions, which seems very relevant for error correction and error mitigation. Yes. So what you mentioned something about unital errors or yeah, I mean, could you please repeat just what were your results? So
so the conjecture is for any channel. The conjecture was that this VLAN index is some big O of D square, where D is the underlying system. So I proved this, but I have to assume that the error model or the noise model or quantum channel is a unital, which means it maps identity operator to identity operator of the system. Which in general, a quantum channel may or may not do that.
So but it's a closed system, or
it's an open quantum system. So your quantum channel is acting on, let's say, mathematically D by D matrices to D by D matrices.
Yeah.
So what I'm assuming here, a crucial part is that it should not only is a completely positive and trace preserving, but it should also map the identity to identity. And channels with this property, I call them unital, because it preserves the unity of the identity operator.
But it would include sort of relaxation or other type of Lindblad operation.
Yes, exactly. So it puts you exactly, yeah. So it puts for example, if you look at the ideal channel, like the unitary conjugation or the identity, that has this property. And if you also take some convex combination of unitary channels, that also has this property. But there are more channels which are unital but don't come like this, and it has a very a significant mass. So there are many unital channels. So it's not that they are very rare. They're in fact quite. They have a non-trivial measure in the set of channels. But it turns out that if you just assume this trace preservation and unitality, then there's a lot of structure that you have from the theory of operator algebras, which I employed here.
Okay, Yaran, do you have more follow-up questions? Maybe Yaran was temporarily frozen. So, or then we can go to Katya, who is a question. Katya, please. Katya? Or is it me who is frozen?
I think I can hear you perfectly. I think
strange, because I see all the other ones.
Oh,
frozen.
That's yeah.
Now, hopefully.
Now I'm back, but
Okay.
it froze for a few seconds, and I had to restart it.
Okay.
Okay.
Same for me.
Hopefully people will be back. But I can I take the occasion. Sorry, Stefan, did you have a question?
I have a question, but by some reason I'm not finding the raise hand symbol.
But go ahead, Stefan. Go ahead, please.
Okay. No, thanks for your talk.
Thank you.
I was curious, well, about several things, but in the next part here, you talked about quantum repeaters.
Mhm.
And you said that when you distribute entanglement in several steps and using PPT states, the states of the resulting state after distribution would be separable. Could you just remind me what was PPT states?
Right. So PPT states is a positive partial transpose. So if you take a bipartite state and you apply the transpose map in one part of the system, PPT states are which that you after you apply the partial transpose, it's still going to be positive. So, for example, if you take a separable state, it will have the property, but there are entangled state with the PPT property. And this whole scheme of quantum repeaters where each sort of try to get the next possible other than separable. So take a PPT entangled state and two of them and somehow use them in this protocol and continue using them. And the hope was to retain the entanglement. But for some reason, every time they did it by hand, they end up getting a separable state. Obviously, that's no use. And so they made this conjecture, which is still an open conjecture, that if you take a 2 PPT state and do this quantum swapping or entanglement swapping procedure, you always get separable.
Okay, but it means if you have a maximal entangled state, this will not happen.
No, exactly. Maximal entangle is not a PPT state. Yes. Yeah.
Thanks.
Okay, we have time for more questions. Yeah, Katya wanted to ask a question, but she's still not back yet. But I can. There is Adam. Adam, please go ahead.
So related to this question from Stefan, does this work if you have if you purify your entanglement along the way? Would that still make it possible to use PPT states, but then you purify the entanglement along the way?
That's a good question. I don't know the answer to this. So the way they used is, but we have to see that if you purify the state and then when you do the repeater, like the swapping, how does the purification respect the swapping operation, right? So that if it's not clear whether after the swapping you still get a purified state, so to speak. So I don't see how would you use this in the protocol. But maybe there is maybe there is a way to do it. But even if you purify a PPT state, and so then that will mean that you'll somehow go from the mixed states to, let's say, purify like a pure state. And let's suppose the quantum repeater, the swapping protocol still holds. You are still asking the question that after you swap, what happens? Do you still retain PPT? And I think this would boil down to the PPT square in a dilated space, probably.
Okay, thanks.
Okay, so for the moment, I think it's in the interest of time, it's good to thank Mizanur again.
Thank you very much.
And we can continue with Adam. So please, Adam, you can share your screen.
Right. Let me just stop sharing and then I can.
Yes. In the meantime, I will introduce Adam. So Adam Kinos, now assistant professor at Lund University, has obtained his PhD thesis from Lund University on imaging in rare earth crystals. And then he stayed in the group in Lund until 2023. However, he also obtained fundings for a collaborative project with a group of Klaus Molmer when he was in Aarhus, so he was also visiting there. And then in 2023 and 2024, he was a researcher at Deep Light Vision, which is a medical company to develop ultrasound optimal tomography as a diagnostic tool. And he started as assistant professor in WACQT in August 2024. So please, Adam, the floor is yours. You're muted.
So thank you very much. I hope you can hear me now. So yes, my name is Kinos, and today I'll talk about advancing quantum technologies and medical imaging using rare earth crystals. So the outline is that I'll begin by giving you a brief introduction to rare earth ion-doped crystals. Then I'll talk about how we'll plan to use these for quantum computing and quantum communication. And then towards the end, I'll mention this quantum biophotonics application, ultrasound optical tomography. Okay, so what are rare earth ion-doped crystals? So a normal crystal is this periodic repetition of atoms in a particular structure. And here, if you have an undoped structure, everything is neatly organized. But when our collaborators grow our rare earth doped crystals, they also use one of the rare earth elements, which are sitting on the first line below the periodic table. And for this talk, I'm going to focus on europium. And when they grow these crystals, these europium ions can replace some of the yttrium ions in this host crystal. And that means that it becomes a little bit more strained because these atoms are not exactly the same size and so on. But you have also these europium ions now sitting inside the crystal. And since each of these ions sees a slightly different environment, they become inhomogeneously broadened. So each of these ions are now absorbing at a slightly different resonance frequency. And this is good because this means that we can address different ions by shining or changing the frequency of our laser. And these ions also have several ground states here, which we can, for qubits, use as zeros and ones, for example, which I'll discuss a bit more later. Okay, the next thing is how these ions can interact with each other. And if we now have our two ions, the green and the blue here, the green ions, or all of these ions, have a static electric dipole moment. So when they are in the ground state, they have a certain electric field surrounding them. And this static electric dipole moment changes when we excite them. So we get a change in the electric field. And if the blue ion here sits sufficiently close to the green ion, it will experience this shift in electric field, and that causes a shift in its transition frequency. So this is a dipole-dipole interaction. So it scales as 1 over the distance between the qubits or the ions to the power of 3. So this means that if we now go in with the original frequency to control the blue ion, this will no longer be resonant. And this is a way that you can use to implement, for example, controlled NOT gates, because if the green ion is excited, you don't do an operation here because it's off resonant. Whereas if the green ion would be in the one state, it would never have been excited, then you could have done this operation here. So then you control the operation based on the green qubit. So why are these materials interesting to research? So one of the properties is that these optical transitions that we're looking at are 4F transitions. And the rare earth has these filled outer electron shells, which sort of act as a Faraday cage to shield them from electrical and magnetical disturbances, which means that we can have very good coherence properties of these ions. So up to 2 milliseconds or so for the optical coherence time. And it has been shown that they can reach up to 13 hours coherence time of their ground states here, these hyperfine levels. They're also spatially close to each other, which I'll discuss a bit later. And this is what allows these strong dipole-dipole interactions here. Another thing is that this inhomogeneous broadening that I talked about is that we can shuffle the ion and optically pump them between their different ground states, and therefore change how the absorption is looking as a function of frequency. And this is something I'll use when I discuss the medical application of ultrasound optical tomography. Okay, so if we now focus in on how to make this into a quantum processor node or a small quantum processor, we start with our crystal here, which is doped, and then we have the inhomogeneous absorption profile. And we find one ion sitting having some resonance frequency here and sitting somewhere in the crystal. And then you can find another ion sitting spatially close so that they can do this ion-ion interaction. And this uses then a different frequency. And then you continue finding more and more of these ions that can interact with each other while also having distinct resonance frequencies, so we can control the different qubits. So the idea is that a single qubit is a single ion inside the crystal. Okay, and if you run simulations on this and showing how many qubits you can find and where they're spatially located. It can look like this. So here a dot represents a qubit, and a line between two dots represents that they can do a good 2-qubit gate. And this is simulations. And here we say that a good 2-qubit gate has a fidelity of around 10 to the minus 3, or an error of 10 to the minus 3. Okay, and the important thing that you can notice here is that we have tens of different qubits here, and the blue and the red are two different protocols for how to find them. As you can see, the blue is more clumped up, so we call this the starfish protocol. It sort of has these arms stretching out like this, whereas the red is more like meandering about in space a little bit more. But regardless of which protocol you choose, you can see that we can have tens of or up to 100 ions or so qubits within tens of nanometers from each other. So we have a really high density of qubits here in these materials. Okay, but one of the problems that we have is that we now know how to address the qubits and how to make them interact, but we also need to know what state they were in. We need to read out if the qubit is in 0 or 1. And this is a difficulty. And it's difficult because we are doing our gate operation via the excited state. So the excited state has to have a long lifetime. Otherwise, we would get a lot of errors. Furthermore, we need to be able to address this excited state from both the 0 and the 1 transition. And that means that we cannot really cycle it. So if we excite it from the 0 to E in the order of getting out a photon and hoping that we will be able to then detect that it was in the 0 state, if it instead falls down to the 1 level, then we have lost all the information of where the qubit initially was, as long as we don't detect that photon. And detecting a single photon could be difficult here. So what we are proposing instead is that we'll switch and use another ion called a neodymium ion, which is another rare earth, which is also doped into the crystal. And we use this as a dedicated readout ion. So this ion now can have a short lifetime, and it can be cyclable. So you could excite it, and then it can fluoresce, fall down, send out a photon, and then you can do this repeatedly in order to collect a lot of photons. Okay, so this seems like an easier choice to detect a readout ion, but of course, at this point, it doesn't really tell us much about the qubit states. So I'm now going to explain the protocol for how we will detect the qubit state using this dedicated readout ion. And I'll first go through the protocol when the qubit is in 0, and then when the qubit is in 1. So if the qubit starts in 0, the protocol is always that you excite from 0 to E. If it starts in 0, that means that it becomes excited. And then it has this changing the static electric dipole moment. And this affects now the transition frequency of the readout ion, which means that if we now try to excite it, it's no longer resonant, and therefore we don't get any photons out. This also means that we should have a short lifetime of the upper excited state, but it shouldn't be too short, because if it's too short, then you have a very large line width, and that means that even if you shift this a little bit, you will no longer, or you would still be able to excite the ions because this line is so broad. So you want a short lifetime, but not too short. Okay, so that means that if it started in 0, we don't get any fluorescence out. If we now run the same protocol, but the qubit starts in 1, the protocol tries to excite from 0 to E. Of course, nothing happens because the qubit is in the 1 state. And so that means that this time when we excite the readout, it will be excited, and therefore it will send out photons, and we can cycle this and get a lot of photons out. So that's how we can detect the state of the qubit by detecting the fluorescence of the dedicated readout ion. So now we've reduced the problem from, instead of doing state selective readout of a single qubit ion, we now want to just do a readout of a single readout ion, which should be easier. But it's still not easy. And this is where we're currently at experimentally. This is what we're trying to achieve, and this is what I want to achieve in my position here as well. So the idea is that we will use a cavity, a microcavity, so it's just a few micrometers long, and one of the ends here will be a fiber, and then the crystal that we use is either a nanocrystal, so a small crystal particle, or a thin film polished down to a few micrometers thickness. And the idea is that we will let this light couple to the readout ion here, And the reason we want to do this is twofold. First is that due to this cavity that we can create here, we get a Purcell enhancement so that we shorten the lifetime, which was good. The other thing is that since we're connecting the ion to this cavity, we also have a higher collection efficiency of the photons that the ions are sending out. So we get an easier time of detecting these this light here. Okay. Another thing that could be interesting now, if we think that we will have all of these qubits now, is to see how they will be arranged in space, but also how they can be connected to each other. So how many other qubits can one qubit on average sort of interact with and do a 2-qubit gate with? And I'm going to start by looking at this line protocol, which sort of meanders a little bit out more in space. And now, of course, we will have our dedicated readout ion close to this qubit so that we will be able to read out the state of them. And now I show this in a connectivity graph where I label all my qubits 1, 2, 3, 4, and so on up to 100. And I show that label both on the x-axis and the y-axis. And then if qubit 23 can do a good 2-qubit gate with qubit number 50, then I'll make a dot there, a blue or a red dot. And again, a good 2-qubit gate would be errors of 10 to the minus 3 in that order. And for those of you that work with the superconducting qubits, which are arranged in this nearest neighbor patterns on how they can interact with each other, then this would be the connectivity graph of that. You would have sort of 4 lines, but it's interrupted at some places because of the boundaries of the edges and the corner qubits having fewer neighbors to talk to. Exactly how this looks depends a little bit on the doping concentration and also the available tuning range of your laser, of how far out you can go here and still trying to find new qubits. But I think we will be in the regime of being able to find tens up to 100 or so qubit, and their connectivity here would be similar to that of a superconducting qubit network. But perhaps a little bit more interestingly is the other protocol, the starfish protocol, where the qubits are more compact, as you saw in the previous image, where we show them in space. And the reason for this is that here we can see that they are much, much higher connectivity because they're all sitting close, and this dipole-dipole interaction is, of course, falling off as 1 over r cubed. Okay, so in this case, we again believe that we can find tens of qubits up to perhaps 100 qubit, but now they will have, each qubit will be able to do a good 2-qubit gate with perhaps 25 or 50 other qubits. So they're very highly connected to each other. So here I just show a bit of the research I've done on this. It's mostly been designing gate operations, looking into what sort of errors comes in, perhaps doing different multi-qubit operations and some experimental demonstrations of this in other materials, looking into this high connectivity and how they are arranged in space, and also looking into some quantum error correction. And if you're interested to read more about the general idea of how this should be laid out, we have a roadmap for Earth quantum computing, where you can just search for my name or search for this and you should be able to find it. And so now, if we say that we can now construct such a quantum computer, there's of course nothing stopping us from constructing another such quantum computer. And then you might be interested in connecting these two to each other. And then you would want to have a quantum repeater structure, which can also be used for quantum cryptography or synchronizing optical clocks. And this is something I've looked into theoretically on how to use such. And in principle, now we want to use a small of these quantum processing nodes inside the quantum repeaters here. And here I've looked into it in a fiber-based scheme. But if we think more as a future vision, we're thinking of putting these repeater nodes up on satellites. So here I'm showing the Starlink low Earth orbit satellite network. It's a few thousand satellites, and these can connect to each other via laser links already. And the idea would now be that you can connect a quantum processor at the ground station to a satellite, and then you can let this satellite just travel around the globe and then connect it back to another ground station somewhere else. You could also connect satellites to each other, but the good advantage of our system is that we could have coherence times of up to 13 hours, and the orbit time of these satellites is 1.5 hours. So we could really just use a transportable quantum memory in a satellite. And our system also already have optical integration built into them in these ions that we're using. Okay, so that was the main focus that I will do during my assistant professorship here. But I've also done research on a medical application called ultrasound optical tomography. So I will also do a bit of this, and exactly how much depends on if we manage to get funding from different positions as well for other PhD students. But I'd like to go through briefly how this works as well. So this is a medical imaging technique. The idea is that you will have some tissue and there might be a tumor there. And you could try to investigate these using just an ultrasound pulse, but perhaps this tumor is reacting to sound the same way as the tissue is. So that means that it can't really be seen on the ultrasound image. So the idea of ultrasound optical tomography is that you would let this ultrasound propagate through the tissue. And then if you want to find out the optical properties of the tissue, then you would also send in light to the tissue here. And this will scatter around the tissue. But some of the light would reach this ultrasound, and there it can interact with the ultrasound and become frequency shifted, as indicated by these red arrows. And the idea is now that the red arrows, we know that these must have come from the ultrasound region. Otherwise, they wouldn't have become frequency shifted. So now we collect the light, both the blue and the red, with a light guide, and we guide it to one of our crystals. And now we use this, the inhomogeneous absorption profile, and that we're able to tailor the absorption for different frequencies. So what we're doing in this crystal is that we're preparing it in such a way that it absorbs all the blue light, but lets through this frequency shifted light. And that means that we only detect the light that we know must have been in this region. And therefore, we get the optical contrast that is also spatially resolved inside tissue. So now we get a strong signal here when the ultrasound is in normal tissue. But if the ultrasound moves to the tumor, where perhaps the tumor have higher absorption, then the red signal decreases because the red photons must have been at the ultrasound, and there we had high absorption, so therefore we don't get a strong signal. So by monitoring this signal as we propagate the ultrasound through the tissue, you can sort of build up an image of how the optical properties looks inside the tissue. So what are the benefits of this method compared to other methods? So this provides spatially resolved optical contrast deep inside tissue. So here is an image of a breast. It's a cross-section of the breast. And white regions here represent higher absorption, and darker regions represent lower absorption. And this is a simulation that we have done. And here is a simulation of how ultrasound optical tomography image might look. And if we overlay them, we can see here we have a stronger signal where we have lower absorption, and we have weaker signal here where we have higher absorption, these whiter regions. So this is actually a way that we can probe the absorption, just as I said before. And if we do this at many different wavelengths, we could also start combining the information of absorption at different wavelengths to say something about what is the water content, lipid content, or so on, and the blood oxygenation that we have inside the tissue. And this technique is non-invasive, non-toxic. It doesn't use any harmful radiation. It doesn't use any contrast agents. And since it doesn't really have any negative effects, it means that we can continuously monitoring the patient and get ideas of if the treatment is working or so on, if we're looking at a cancer treatment or so, for example. So the clinical potential of this, if we just focus on measuring the tissue oxygenation, if we have lack of tissue oxygenation, we could think of applications such as stroke or myocardial infarctions or heart attacks, or as I mentioned, breast cancer or cancer in general. So my research on this topic is a few articles from the recent year, and we also have a patent application for this company, Deep Light Vision, which is working on developing this, and this is where I've worked for the past year. as well as a lot of different conference papers on this topic. So to summarize, what I want to do in my assistant professorship here is we want to start to detect these dedicated readout ions. Then we want to do ion-ion interactions between first the qubit ions and the readout, and then between different qubits. Then we want to figure out how we can connect all of these to each other and monitor their connectivity. And for future applications is also thinking of using them for quantum repeater structures, both in fiber-based, but also in space. And then I'll also do something with ultrasound optical tomography and developing this technique further. So with that, I'd like to thank WACQT and Knut and Alice Wallenberg's Stiftelse for funding this position and Lund University for hosting me. And I'd like to thank you all for listening.
Thank you very much, Adam, on behalf of all the audience. Are there any questions for Adam? So I see a lot of applauses as reactions. Let me start with a question then. In the part where you are interested into, applications to quantum computing, so I see that you can do 2-qubit gates, maybe with a quite flexible connectivity, and then you can also, you have ways to do single qubit gates, but can you do arbitrary single qubit rotations, or are there limitations?
We can do arbitrary single qubit rotations, and we can do controlled arbitrary qubit gates as well. So 2 qubit gates can be controlled arbitrary.
Okay. And that was already published, so it's already...
Yes, we have some, I have a collaboration with Klaus Möllmer where we discuss things like this, and it's also in other papers about how to...
Experimentally also?
Not experimentally.
As a proposal.
There has been work on implementing experimental gates where a single qubit is an ensemble of ions. So there are millions or billions of ions all collecting, working as one qubit. And then we have shown single qubit operations. But it has not been shown experimentally in this single qubit state from our group.
And this is something that you want to do?
Yes.
Okay, great. Thank you. Yes, we have Katja who is asking a question. Please, Katja.
Yes, thank you for the talk. I was also curious, maybe in a similar direction, but more experimental, about the connectivity. Then this is essentially determined by the way in which the crystal growth or the doping concentration is, right?
Exactly.
And then the addressability, in a way, also the way in which you build connectivity is an experimental issue where you go spatially selecting an infrequency, right?
Yes. So this would be different for each crystal and how exactly what part of the crystal you find. So you would need to start each of your quantum computer, you would need to start to calibrate it by finding where exactly, at what frequencies can you address the different qubits, how are they connecting to each other, how strongly are they connected, and so on. But since this is a solid state material, you have a crystal there, we don't expect this to change over time. So as long as you've done it once for your computer, it will sort of stay that way.
But the network structure is, let's say, not deterministically set as you would do with conducting qubits. Is essentially you first need to map the whole and then essentially build the experimental setup to control it, and also how to use that specific connectivity that comes, right? Yes. And my question is then scalability. Besides possible crosstalk that can come from, let's say, not controllable a priori connectivity, right?
Yes, so you would need to be careful to avoid crosstalk, and this is something we've looked at theoretically, but again, we haven't been able to measure it experimentally. We need to detect a single ion first before we can do that. But yes, so you need to consider minimizing crosstalk between the different qubits and also the other ions that you have in your crystal. Another approach that you could take is to try to implant your ions, so you have a purely crystal without any dopant inside of it, and then you implant the ions afterwards, and then you can have more control over exactly how many ions you put and where you put them. The problem is that currently this technique gives worse coherence properties. So when you implant them, it's destroying the crystal a little bit. And even if you anneal the crystal afterwards, they have not been able to restore it to that level of coherence properties if you grow them from scratch.
We are doing that in thin films. It seems to work, but indeed we go the other way. No, thank you for the answer.
Yep, that sounds very interesting. I would like to hear more about that, but yeah, thanks.
Okay, we have Yaran as a question.
Yes, thank you very much for a very nice talk. I just so you are sure about the fact that your qubits do not drift? I mean, superconducting qubits certainly are that solid state, but they do drift noticeably.
Yes. So okay. So I shouldn't say that they don't drift. There has been people looking at single ions in other labs, and then they have seen some spectral diffusion of them drifting around. In the most part, I think this has been due to surface effects. So they have used other techniques, which means that they probe ions that are much closer to the surface, and then these effects could come in. This could also be a possibility or a risk if we use nanocrystal, because these are also quite small, so the surface is close. But if we use a thin film, which is several micrometers thick, then perhaps we could avoid this.
Thanks. So I also have I really like to think, I mean, your idea of sending quantum information around in quantum memories around the Earth with satellites. How far are you in? Do you have already space on a future rocket, or how far are you with these plans? And what's the global state of the art here? What are your what's the competition? Because this seems like a really nice idea.
So this is more of an idea stage than actually sending it up on a satellite stage. So right now we would need to do first theoretical work, which I'll start do, or my PhD student will start do, on exactly how this would scale. I've looked at it for fiber-based, and we believe we can use the same ideas, but now for satellites. But of course, there's other complications you would have to look into there. The current state of the art is that there are groups that have done this with satellites. The problem is often that they need to connect it several times up and down or between satellites and so on, and then you get a lot of losses. Whereas we believe that we can use a transportable quantum memory, then that you don't have to have as many links and still reach a global scale. So that I believe could be the advantage here.
So what you say is, I mean, there is of course the Chinese satellite, right?
Yeah, exactly.
But no one has sent up a quantum memory like you suggest.
No, so this is again, the idea would be to have a quantum memory there, but we would first need to show that we can build one of these small quantum processors, that it works the way we want them to work, and that the connection to the readout ion works, and so on. And then it would start being in a lab, of course, to build up one of these structures where we have a cavity where you can send out a single photon and get a click, and you can detect that reliably. And then, of course, you want to duplicate your setup so that you can get sort of one repeater node where you can entangle the photons and entangle qubits in different processors nodes, all on ground first. And then after you've shown that, then you can start thinking about what would happen if we put this on a satellite.
Thanks.
Yeah.
Thank you very much, Adam. So thank you again.
Thank you.
On behalf of all. So then in the interest of time, I would like to invite David to, or David to put his presentation on, to share the screen. In the meantime, I will introduce him. So that David obtained his PhD from Lund University in the group of Henri Yeh on attosecond physics. And then he obtained an international Vetenskapsrådet VR grant that allowed him to move to Germany in Freiburg for 2 years, and then to come back to Lund, where then he became assistant professor in WACQT since September 2024. So please, David, the floor is yours.
Thank you. Thank you for the introduction. So Yes, so I will be presenting my research project for this position, which is ultrafast quantum photoelectronics, which is really at the interface between attosecond physics and more quantum information. So I myself come more from the atto science, atto community, where the idea is to use very short pulses of attosecond duration to look at how electrons move in matter, in atoms, in molecules, and how they drive chemical reactions, etc. But recently there has been quite a lot of interest on trying to understand more from a quantum information perspective these processes, such as what is the role of entanglement between the different degrees of freedom that you have in molecules, etc. How does decoherence come in? Can we probe it in time? And so this is a rather recent development in the ATO community, and this is really where I want to go. So I will start really with the basics so that we all get on the same page, and then I will try to explain a bit what I have done and where I want to go. So here you have a picture of an atom. So you have bound states and the electrons in the bound states, and then at some point you reach the ionization threshold, and then now you have a continuum of states. And so we all know that if you have short frequency light, so high photon energy, you can take one electron from a bound state to the continuum, and then this electron will leave. It's called a photoelectron. And then if now you measure the speed or in general the photoelectron spectrum, what you will see is that you will have a very sharp line corresponding to electrons that have an energy which is given by this very simple formula from Einstein, which is just the photon energy minus the ionization potential. And this you can almost understand just classically with picturing the electron as a little point-like particle. Now, in practice, the electron, of course, is a quantum object. So this would be one way to describe your photoelectron, where it has a certain amplitude A, and it also has a certain phase, which is a scattering phase. Now, in practice, you can only measure the amplitude. Here, the phase, you simply do not have access in the case where you just populate the single continuum states. Now, the difference is that if instead of using monochromatic light like synchrotron radiation, now you start using short pulses because of time bandwidth product or Fourier transforms or whatever you want to call it. These short pulses, they have a very broad spectral content. So they're very broad, and what will happen is that now you will populate a lot of continuum states here. And then you will have a phase that might vary across the entire spectrum. And then it's very tempting to write your photoelectron like this. It's just an integral over continuum wave functions that I just label with their energy here, which have a certain amplitude and a certain phase. And so for people coming from the optics community like myself, I mean, this is really looking like how you would describe a short pulse. And so that's basically what has been going on, I would say, in attosecond physics now since the last 20 years. The idea was to try to characterize the spectral amplitude and phase of these photoelectron wave packets. And once you have fully characterized it in time, in the spectral domain, then you can have access to the temporal properties. You can look at photonization delays or other photonization dynamics. But the problem is that this might not always hold. So if now instead of ionizing an atom, let's assume now that we have a molecule, a diatomic molecule, and I ionize it from here, then I might get this electron wave packet here. But of course, now my molecule is vibrating, right? So I could also ionize at a slightly different time, where now the two nuclei are spaced a bit differently. And then now my electron wave packet will be a little bit different, might have different energy, might have different phase. And then at yet another internuclear spacing, I might have yet another wave packet. And in practice, because we cannot see, we don't know what is the internuclear spacing at the time we're ionizing, then what we get is this mixture of all the states. And so now you can see that asking, okay, what is the spectral amplitude and what is the spectral phase of this mixture is maybe not a good question. So if we want to properly characterize what is the state of the photoelectron, then we need to measure the photoelectron density matrix. And this is something that we started thinking about in 2022 or maybe even before. How can we try to measure the reduced photoelectron density matrix? So here's the idea. You have a short pulse that ionizes your target, and now you will populate a broad distribution of continuum states. So in the terms of the density matrix, what you can do is you just take a spectrometer, you measure your photoelectron spectrum, and this will give you access to the diagonal elements of your density matrix, where here in both axes I have kinetic energy, because this is how I label the continuum states. I just label them with the energy that they have. So the question is, how do I access these off-diagonal elements? Well, the idea that we got was, okay, let's use two infrared pulses with slightly different frequencies, omega 1, omega 2, such that the frequency difference is called delta omega. So what will happen is that then we can couple two different intermediate continuum states here to the same final continuum state epsilon f. And then if we change the delay between the XUV pulse that we use to ionize and the bichromatic infrared field, then we will see oscillations of the photoelectron yield here, which you can show is proportional to the magnitude of the density matrix element with epsilon 1, epsilon 2, times cosine modulation as you change the delay, which oscillates with frequency delta omega, and with the phase, which is the phase of this density matrix element. So this means that now we have access to one off-diagonal element of this density matrix. Now in practice, because we have broad pulses, so we cover a lot of continuum states, which means we also have a lot of different final states. So then we can resolve it as a function of the final energy, look at the amplitude and the phase of the oscillations as a function of final energy, and now we get access to a full subdiagonal. And because the density matrix is Hermitian, we get for free the symmetric off-diagonal. And then what you can do is that then you change the frequency difference between your two infrared lasers. So now let's say you increase delta omega, and now you get access to new subdiagonals. And then if you repeat this many times, you build your density matrix. So that was the idea. And in our community, we always have to give it some animal name. And here it's called Kraken. It's not the best acronym, but it's quite catchy and everybody remembers it, so we kept it. So, okay, that was the idea. Now here are the experimental results that you can find on arXiv and are now finally more or less accepted in Nature Photonics. So we did measurements in two different atoms, in helium and in argon. So here, this is the raw data. This is what I show on the top row here for helium and here for argon. So the problem that you can see that we don't reconstruct the full density matrix, and the problem is that we're dealing with continuous variable because the energy, the photoelectron can have continuous energy distribution. And so in principle, we would have to do an infinite number of measurements. So in practice, what we do is that we measure the populations here in each case, and then we do a finite number of measurements. So here, 6 different measurements that give us access to the 6 of diagonal elements. So now already just based on the raw data, you can see that the partially reconstructed density matrix in helium and in argon, they look quite different. In helium, it almost looks circular, while in argon, it definitely looks much more elongated. And then what you can do is you can use, for example, Bayesian estimation algorithm to try to reconstruct what is the most likely density matrix underlying these measurements. And this is what I present here. This is the density matrix in argon, in helium, where you see that it's really circular, which is indicating that we have more or less a fully coherent state. While in argon, we clearly see that this density matrix is elongated, and the anti-diagonal extends much less than the main diagonal. So then using this data, then we can calculate what's the purity, the photoelectron purity in helium and argon. And experimentally, we got a purity of 0.94 plus minus 0.6 in helium compared to 1 based on theoretical calculations, while in argon, we get 0.65 and the theory predicts 0.66. So this is very good. That was really that it really allowed us to benchmark this technique and the accuracy that we can reach. And now the question, why do we get a pure state in helium and not in argon? So in simple terms, in argon, when we ionize from a 3p6 shell. So we end up with total angular momentum for the ion, which is L equal to 1, and the total spin, which is equal to 1/2. So then we get spin orbit splitting, and we can have total angular momentum J equals 3/2 or 1/2. And depending on this, the ion will have slightly different energy, and accordingly, the electron will also have slightly different energy. So the total ion plus photoelectron system can be written like this. Either I leave my ion on with the J equals 1/2, and then my photoelectron will have a certain kinetic energy, or I leave my photoelectron with J equals 3/2, and my photoelectron will have a different energy. So we have an entangled state, and then since we only measure the photoelectron, then we have to trace over the ionic degrees of freedom, and then we end up with a statistical mixture. And this you can see here both on the raw data and on the reconstructed density matrix, that you have essentially two coherent states, a bit like helium, that are separated here, which corresponds to these two different ionic states, J equals 1/2 and J equals 3/2. But it's a statistical mixture, and this is why we get a reduced purity. So this is what we have achieved so far. So where do we want to go? So the idea is to really continue and develop metrology, quantum metrology for photoelectrons. I will give an idea of where we want to go. And once we have these tools, we want mainly to apply it for different aspects. So one aspect is doing high harmonic quantum state spectroscopy. So using this photoelectron quantum state tomography to really look at the quantum properties of light, of attosecond light pulses. Then we also want to do photoelectron quantum state spectroscopy. So we showed here, this was the first demonstration that, okay, the quantum state of the photoelectron depends on the species that you're looking at, helium or argon. So if now we look at molecules, then depending on the molecule and what is going on in the ion, as I will discuss, we expect to see different quantum states for the photoelectron, and we're hoping to be able to learn more than using just classical photoelectron spectroscopy. And then the last aspect is really trying to do more fundamental quantum information, quantum physics experiments with photoelectrons. So regarding quantum metrology of photoelectrons, what do we want to do? Well, the key thing is that we want to be able to speed up these measurements. These are very time-consuming measurements. It takes about 7 hours to do the tomography, the partial tomography for a single atom. for a species, and then we have to repeat this in the same conditions for the different atoms. So it's very time consuming, and it puts huge constraints of stability for our laser systems. So what we want to do is to speed up, and how do we do that? We basically add more arms to our Kraken by adding more frequencies. So instead of having just two different colors, now we can have 3, 4, 5, 6 different colors. That will induce different beatings. So I will have a beating between these two, and beating between these two, and these two, and these two, etc., etc. And if you choose wisely the different colors, the different frequencies, then you can make sure that you have no two pairs that give you the same beating frequency. And then now when you scan as of the delay between your polychromatic infrared and the XUV, you will get this very complicated spectrogram here. And once you Fourier transform, now you will get all these different beating frequencies that appear. So where before we would have to do 7 different measurements, where in each case we would just get one of these beating frequencies, now we get all of these in just a single measurement. So we have already tried. So this was using 4 different colors. And here is the spectrogram that we acquired. So you see it looks quite complicated, but then we could really go and isolate these different beating frequencies to try to and then use it to reconstruct the density matrix. There were problems that we still have to solve. But at least this shows that in principle, this is viable, and this would really allow, in this case, to speed up the measurements from about 6 hours to 1 hour in this case. So that's one aspect that we want to work on. And then once we have these tools that are available, then we want to apply them. So the first case, as I mentioned, was to do photoelectron quantum state spectroscopy. So let's imagine that I have a short pulse, and then here I have a molecule. So here in blue, it's the electron cloud, and then I have these 2 nuclei here. So when I will ionize it, I will get a photoelectron leaving, and then I will get nuclei that move, the electronic density that is changing as well. And so what will happen is, the question is, how does the electronic motion, the nuclear motion, how does it affect the photoelectron? What will happen is that in many cases, this will result in entanglement between the photoelectron and the molecule. And so the question is, if we are able to properly characterize the quantum state of the photoelectron, can we use the fact that the electron and the molecule are entangled to probe indirectly the dynamics going on in the ion, how the nuclei are moving, how the electrons are oscillating on the attosecond to few femtosecond time scale? And also, does the entanglement, does the degree of coherence of the photoelectron, does it evolve over time? How can we measure it? So these are some of the questions that we want to address. Another aspect is high harmonic quantum state spectroscopy. So here I didn't explain how higher harmonic generation works, but in short terms, what happens is you have a very strong infrared field that excites an atom or a molecule, and it will be so strong that it can bend the potential, the atomic or molecular potential, such that now an electron can tunnel through the barrier. It's accelerated by the laser field, and then it's driven back to the molecule. And then when it comes back, it emits light. So this is basically what happens, except that in a molecule, again, while the electron is traveling, the molecule itself is changing. The nuclei are moving, the electrons are moving. And what will happen, there's been a few theory papers discussing this, is that you will end up, in most cases, producing light that is not necessarily pure. It might be a mixture of different states. And again, you have the light that is produced is entangled with the electronic state of the atom that is left behind. So then what we want to do is now we want to use helium that we know is very nice, doesn't introduce any decoherence because of its properties, etc. And we want to use this light to ionize helium and get a photoelectron out. And so the question now is, what is the quantum state of the photoelectron now that we use this weird non-classical light? Did we swap the entanglement between the molecule and the photon to now the molecule and the electron? And in general, can we use non-classical light, quantum light, to control the photonization process? And then finally, the last aspect is to try to do quantum experiments with photoelectrons. And it might be very counterintuitive at the beginning because we start with a huge number of photons, something like 10 to 16. However, higher the harmonic generation is very inefficient. So we'll lose about 8 orders of magnitude. And then the photonization cross-section is also very low. So in practice, in the experiments, we have between 1 to 2 or even less than 1 electron per shot. So we're really in the regime where we really create single photoelectrons. And so can we use now the single photoelectron source for fundamental quantum information experiments? And two ideas are to do slit experiments to test quantum mechanics. I will just say a word about this later. And the other idea is to try to generate double photonization, single photon double ionization, create 2 electrons and try to see if they're entangled and study their properties.
Sorry,
so very quickly.
Just to let you know, sorry to interrupt. You have 3 minutes more or less.
Yes,
to conclude.
I finished. This is one of my last slides. Sorry. So the idea here is that we have a photoelectron that goes through 3 slits, and then we will get interference. And Born's rule, basically, and this is based on Born's rule that just tells us that the probability is the modular square of the wave function. And it prevents third order interference. So in term, that would be the product of the 3 wave functions, psi A, psi B, psi C. And so this can actually be tested if you do several measurements with different slit configurations. You measure the probability to detect an electron whether you have all slits open or only 2 or only 1. And so we did some first tests where we could create these slits by now using 3 different colors that we can block individually, see the different configurations, and then see if we can validate Born's rule or not. This has been tested already in the past with other photons, etc., but never with photoelectrons. And because I'm running out of time, I will just thank all my colleagues throughout the years with whom I discussed a lot, and many of these ideas came from discussions with different people. And of course, I thank WACQT for funding this project, and thank you for your attention.
Thank you very much. Are there questions for David? Yes, we have Joran. Go ahead, Joran. You're muted.
I was going to applause, but I also have a question. You mentioned, so thank you very much for a very nice talk. You mentioned that you get entanglement between the molecular vibrations and the photoelectron, and that this happens on the attoseconds to femtosecond time scale. But molecular vibrations are typically slower than femtosecond, right?
No. I mean, it depends. If you take uranium-2, it's very slow. If you take H2, it's a few femtosecond period for the stretching. So if you take small hydrocarbons, methane, etc., there you can have very fast vibrations.
Thanks.
Katja.
So thank you for a wonderful talk. I have just out of curiosity one question about your tomography, your mapping of the density matrix. And I understand why there is a band closer to diagonal where one cannot access the elements because you cannot get too close in frequency, I would assume. Is there any way around that, or to reduce that kind of dead band around the diagram?
I mean, so you can try to get closer and closer and closer, which means that you will have oscillations that are slower and slower and slower. The problem is that at some point these oscillations are so slow that this is also comparable with like other things that are oscillating very slowly in the lab, and then everything is oscillating. So yeah, getting very close to the main diagonal is really challenging from a purely technical point of view. And then the reason why it doesn't extend further here is because, well, we have a certain range of frequencies that we have in our laser. It has a certain width, and then we cannot go outside that. So one of the objectives is to actually broaden the spectrum to be able to sample further away.
Thank you.
Per.
Yeah, so thank you for a nice talk. So my question is related to this, the speed up of your tomography. So if I understood it correctly, you had 4 different frequencies here, but what sets the limit on how many frequencies you can choose? I guess you partly gave the answer in the previous answer, but maybe you can elaborate on this.
Yes, so partially, I mean, there are different things. There's because the way we create all these frequencies, we have very short pulses that are spectrally broad, and then we have devices, I will not go into detail, that allow us to go and select specific frequencies inside this broad spectrum. So one limitation is that the width of the spectrum, so we're working on getting something broader. Then we could also say, okay, I can reduce the width of these different colors, because I mean, I say monochromatic, but compared to what Adam is doing, we're still broadband. So you could say, okay, let's have thinner and thinner frequencies and I mean gates, and have many more of them. But then this is still a nonlinear signal, right? A nonlinear process. So we still need to have high enough intensity to have 2-photon absorption. And then the last thing is, if you have many different frequencies, then you need to scan the delay with very small steps so that you fulfill the Nyquist frequency for the faster oscillations, but you also need to scan for very long for the slowest. So then it becomes very time consuming, and then maybe you don't really gain that speed up.
Okay. Oh, thank you.
I still haven't found my raised hand, but if there's time,
Yes, go ahead. This would be the last question. Go ahead, Stefan.
Okay, so I was curious about the discussion about molecules you had in the beginning, because you may ionize at different distances between the nuclei, which means that I suppose that your density matrix will be taking an average of the density matrix for the nuclei at each position.
Yes.
Yes. So would it be interesting or possible that you actually sort of time it with the vibrations, so you could get how does the density matrix change as the nucleus moves?
I mean, what I have to say is that for now, we're looking at the asymptotic density matrix. And how to look at it time resolved is really a big question, because we detect the electron a millisecond or hundreds of microseconds after. So a lot has happened, and then what you measure is essentially at t equal infinity. So there is a lot to be done. There are some ideas, but yeah, it's interesting but a tough question.
Okay, thanks.
Okay, so I would like to thank again David, but also all the other speakers from today's symposium. We look forward to meet you in real life and have more interactions. So with this, yes, I can conclude the symposium, and I really look forward to interact with you in person. Thank you very much, everyone, and we can run to the reapplication meeting. Okay.
It's very nice to have you all in WACQT.
Indeed.
Thank you.
Yeah, welcome to WACQT, indeed.
Thank you.
See you soon.
Thank you.
Bye.
Bye.
Bye.